area of dynamical systems with respect to what we used to study in our course, but I think it's important that you have an idea of very different branches of the mathematics we are interested in. So please, Nikita,
okay,
you can start.
Let's start. The name of our talk is finitely smooth normal forms of local families of vector fields. I need to define every word that emerges in that name. So let's start from local families of vector fields. Local means just that we use germ on phase space and germ on parameter space, and that's just a vector field that's dependent on the parameter. So the second, why we need the normal forms? Normal forms is just some simpler cases of these local families that easier to study. And the second definition that I need, that probably I won't use anymore, it's just that equality of local families of vector fields. It's I will write in this way. Two local families are equal if there exists homeomorphism of phase space and homeomorphism of parameter space that conjugates vector fields of these families. And of course we need to... It's a homeomorphism of phase space.
What is this phase?
Phase space is just X. X is phase space, epsilon is parameter space.
So
Phase.
the homeomorphism of the phase space that depends on the parameter.
On a parameter, yes.
One parameter family of homeomorphism. It is automorphism.
It needs to be homeomorphism only, but yes, it's actually automorphism.
You just can consider some vector fields and R. N and R n.
And we need to map zero parameter vector field to a zero parameter vector field. It's just well, it comes from this definition that we need to conjugate zero parameter vector fields. Okay, I said that I probably won't use this definition anymore, so let us go next. We will talk a lot about resonant and resonances. The first, vector field in singular point, it might be written in such form. I'm sorry. That's just a linear part of a vector field in a singular point. Any vector field might be written in this way locally. So it's not a not a hard part. So we will set all our vector fields, all our linear parts to be diagonal and with different eigenvalues. So the resonance it's when some eigenvalue equal to other eigenvalues with some coefficients. That coefficients must be integer numbers, and sum of, I will next write it in this way. So the norm of R must be not less than 2. That emerges when we solve equation for a series of, well, let us stop here. The theorem that we will try to prove today, it's when eigenvalues form non-resonant set, we local family that is a deformation of such germ with non-resonant eigenvalues is smoothly equivalent to just family that is given by this equation.
Sorry, what you mean by, could you please repeat the definition of resonance?
We have linear part of a vector field in a singular point. It is diagonalizable. So resonance it's when some eigenvalue equal to sum of our eigenvalues with integer coefficients. Well, I'm sorry, not integer, but integer resonance.
From this definition, every eigenvalue is resonance because lambda g is just lambda g.
But we need norm of R to be not less than 2. So we do not allow such case. So when eigenvalue is non-resonant, our local family is that is a deformation of vector field is smoothly equivalent, finitely smoothly equivalent to such family. I can write this theorem.
What do you mean by finitely smooth?
This homeomorphism that I wrote here, it might be finitely smooth. So that's n that comes from this homeomorphism, it gives us finitely smooth equivalence. And the second theorem, then well, no.
Is it true that this assertion must be valid for epsilon small enough?
Yes, it's we only look on the families local on parameter. The second theorem is a bit trickier, so we will need one more definition. It's a definition of strongly single resonance set. We probably can get some resonance with eigenvalues of general case when we look at the linear part of a vector field. So we will look at a special case when all the resonance are just emerged by one equation that is generator of these resonances. So local family of vector fields, which is a deformation of germ of vector field linearization of which have only one generator of all resonances is and hyperbolic.
You mean one dimension or what?
What do you mean by one dimension?
No, sorry, I understood you incorrectly, but is this just a scalar product of two parameters?
Yes, it's a scalar product.
But if you have some resonance family, you can multiply some parameter by
Part.
so you have one-dimensional family of resonance.
Yeah, we have a family of resonances generated by this equation. Yes, that's true. So when we have family with linear part with strongly single resonant set of eigenvalues, then this family equal to such equation where G is a polynomial dependent on a scalar variable that is XR. The first definition of let us start main part. It's first lemma, and first lemma needs some definitions too. The first deformation of vector field is such local family. So we deform a vector field with linear part A0 when we have zero parameter, we need deformation to be 0, and not only deformation, but it's jet. It's one jet, or first derivative. It must be done to not affect linear part of a vector field that are already dependent on a parameter. And the second definition, preliminary normal form. This is already nearby from results that I declared in the beginning. So preliminary, I will need much more space. Preliminary normal form is such normal form So I will add some in words. The P is a polynomial that we put all resonant monoms that emerge in this normal form to this polynomial, and omega is omega has n0 jet. Then, okay, I need a bit. It's a preliminary form, preliminary normal form of order n, so that degree of this polynomial is not bigger than n, and omega have n0 and jet in origin, and I will write it. Also in this form we need coordinate planes in decomposition of phase space to be invariant for all vector fields in this form. That can be we can get it from stable and unstable manifolds decomposition of phase space. and and also we need one jet of polynomial p to be equal to 0. That means that we can get ну, я скажу на русском. У нас не может быть резонансов степени меньше 2 по определению. Резонансы стартуют с степени 2 и не меньше. Соответственно, полином π содержит в себе резонансы и начинается со второй степени. And when P is strongly single resonant, P begins to equal to multiplication of X, that is a diagonal matrix for, it's just to G that is a polynomial dependent on resonant monom. So the first lemma is that this definition equal to this definition for non-resonant and strongly single resonant vector fields. The first to prove, I will remove this. First, we need to place first definition first definition allow us to allow singular point to move from genus, so we need to place it correctly. And first part of proof is that by implicit function theorem, we just solve this equation. And just place singular point our origin of vector field to a solution to this equation. This equation have a solution by implicit function theorem. So the second we can use stable and unstable manifolds decomposition to place coordinate planes correctly to make them invariant. Third part, by Poincare-Dulac theorem, we can use, we can remove non-resonant monomes from series of vector field. So we will get needed decomposition. And here I will speak about Poincare-Dulac theorem that will be a bit easier. In Poincare-Dulac theorem, we solve such an equation. And explicitly write down equation for homeomorphism. And solve it. The first thing to do is use special case for homeomorphism. We decompose it as identity plus something small. And then so I decomposed H. The next So solution to this equation is equal to solving such functional equation. Tak, tak. And instead of solving this equation, in Poincaré-Dulac solved it gomologically. They solved equation in this form, and instead of solving functional equation, they approximate its solution by method of successive approximations. By solving these equations in this form. And it might be written in this form. So we step by step approximate our H and F. So by method of Poincaré-Dulac, we make our polynomial consisting only of resonant monoms, and jet of omega make equals to 0. The next lemma will be without proof, but right now we already showed that for non-resonant case we already acquired a form that we needed, because polynomial in non-resonant case is equal to 0 and omega in non-resonant case, so we can make as large as we can. And for n jet of omega we can make as large as we can, as we want. And and the case for strongly single resonant case is completed by such lemma. the first we differentiate equation in form that they got in here. We got a series SG, so we have equation for this series. We differentiate.
And on the left you have also the same x, yeah?
Yeah.
The vector, different size.
Yeah, it's diagonal matrix constructed from x coordinates.
Yeah, but у вас просто функция разного размера, но не красивая.
Ну, окей.
Это разница.
Конечно, это разные функции.
Ну, то есть подчеркивается, что это матрица, то есть вот все. We differentiate our resonant monom, that is here, and we just get and we put this equation in system and get factor system of these equations. That is some new function f that is given by series, not a polynomial yet. So the lemma 2 is saying that consider semi-formal. Well, semi-formal I didn't give it. Let us consider family in form such way, and corresponding factor system, that is then if mj for some mj of f is invertible, that is f is equal to c is just non-zero jet of some m. When mj of f is invertible, then we can make such substitution of variables that semi-formal, that family in a form, let us mark it 3, might be conjugated to family in preliminary normal form that I wrote here, with polynomial p equal to polynomial of degree 2m instead of n. That means that when we get a single resonant, strongly single resonant case, we can make this polynomial with resonances here of degree 2m, where m is degree of function f that emerges when we look at factor system of our original system. So here I want to stop.
Okay, thank you. Do we have any questions? Comments? Thank you very much.